Hello everyone, welcome to the course. Welcome to the lecture. Actually, we are starting now from the next paper in our series. So, first 6 weeks they were spent for the first paper. Now, I have released the reading note submission. For reading note submission is open for this paper. It is due on day after tomorrow, right? But if you look at the format of reading notes now, I have changed the questions, right? So actually, maybe it is better if I share with you the uh, new reading note format because the questions they are different from the previous ones. It is not like exact same questions here. So let me do the preview here. So you need to answer all these questions, and so basically what you need to do is that you need to complete the paper reading carefully, understanding it, and then answer everything. And I have distributed the points for each question, and for those questions where you have like multiple sub questions, so points are allocated for each of those sub questions as well. Okay, so yeah. So this was one information which I wanted to share with you. And now we can start our lecture. I am assuming everyone is able to see my screen and hear me clearly. Please confirm that so that I am sure and I can continue. Everyone can see my screen and hear me clearly? Okay, thank you. Thank you. Okay, so uh, So the first slide, basically, the paper we are going to discuss is a survey of microarchitectural side and covert channels, attacks, and defenses. So this paper was published in 2018 in Journal of Hardware System Security. So the motivation behind writing this survey paper, again, this is not a research article. It is a survey paper. So it doesn't present a new attack or it doesn't present a new defense, but it provides a condensed survey of existing literature. So the motivation is to provide a survey of microarchitecture characteristics, which basically enable the side channels, so timing-based attacks and defenses against them, against like those timing-based attacks. Uh, and as a result, it offers a better insight to researchers and developers to understand that how their software will behave and how it can become susceptible to security attacks, right? So, for example, if you understand that how the microarchitecture details of your platform can be exploited by an attacker to launch an attack on your software which is running on that platform, if you know it, or if you know the basic approaches or common characteristics of the platform which are exploited by the attackers, then you can take some defensive measures to protect your programs or processes running on the hardware, right? So as clear from the name, this paper covers first talks about uh, covert channels, covert channel and side channels, and how microarchitectural components or microarchitectural features they enable these covert and side channels, and then it talks about attacks like provides analysis of the existing attacks and defenses against them. So, uh, I will like try to cover as much of the paper as possible. And tomorrow we have a student presentation. Sorry. How can I exit this? Right. Yeah. So tomorrow we have a student presentation. So I will spare last 15-20 minutes for that. But other than that, remaining part of the lecture we will in the remaining part of the lecture tomorrow we will continue covering this paper. Okay. So if you have like I'm starting from the introduction. So like if you have any questions in context of like the introduction section, I hope you have read the at least the introduction paper, if not the full paper, introduction section, if not the full paper. So if you have any questions from that sections, please go ahead and write them in the chat, right? I will take care of them after covering the slide. So uh, timing based side and cover channel attacks, we will talk about them in more detail, but first let's talk about why they are critical, because these attacks cause leakage of private or sensitive information. How? That we are not going to talk about right now, but later, maybe tomorrow or in some future paper, right? When we actually see a complete implementation of our complete working of a attack. Uh, these kind of attacks, which exploit the side of the cover channels, they do not need the physical proximity to the victim. So to the victim process, though. So victim process is one on which you are launching the attack, right? And attacker process is one which is launching the attack. So so they do not they do you do not need any how to say uh, like uh, you do not need your adversary to physically access your machine. It is enough if the process of the adversary is running on the same machine on the same machine as the victim process, right? So that is known as co-location. So where the victim process and the attacker process, they are running on the same machine, but the person who is launching the attack does not need any physical access to the machine. So some of those attacks which exploit side channels and covert channels, they even do not need the co-location, which basically mean that attacker process, it may be running on a remote machine, so on two different machines but connected through a network. So uh, it is difficult to hard with this type of attacks. These type of attacks mean the attacks which exploit or which rely on covert and side channels. So it is hard to deal with them without increasing the performance degradation. Like you can develop the defense mechanism against them, but those defense mechanism incur some performance overhead. Lower the performance overhead, better is the defense mechanism, or more preferable is that defense mechanism. Okay, now uh, before we talk about side channel and the covert channel, let's first talk about what is the communication channel. So the idea of the communication channel is that it is a logical link between a sender and a receiver entity to transfer information, right? So the communication channel is like a general idea, right? Even like not if you and we are not talking in context of the security attacks. We know what is the communication channel. On one side, you have a sender, on the other side, you have a receiver. In between, you have some kind of connection between them to transfer the information. Now, covert channel and side channel both are have one common feature, that both of these channels are originally not intended are designed for information transfer. They are not by design. Their purpose is not to transfer information between two entities. However, they end up transferring information from one point to the other point, or from sender to the receiver. So that is common. Like by design, they are not intended for transfer information. But what is different that in covert channel, uh, covert channel is discovered or abused by an attacker. So the way a hardware component is meant to use, uh, it is not used in that way, in the desired way, or it is abused by the attacker. And the other thing is like the other feature of the covered channel is that sender, that is the attacker, it intentionally sends information over the channel, right? But in case of the side channel, still there is information, definitely there is information transfer, but sender, which in case of the side channel is not an attacker but a victim process, the victim process unintentionally sends information over the channel. as a side effect of implementation and how it is using the hardware component. When we will see another paper where actually L1 cache is used to launch an attack, then you will see in more clear way what we mean that a sender unintentionally send the information to the receiver as a side effect of using the caches. So uh, in side channel attacks, as I said, victim is the sender, while attacker is the receiving process. So the when we compare the side channels with the covert channels, we find that side channels are more hard to detect because these side channels are doing the information leakage unintentionally. In context of the covert channels or side channel, an important parameter is the channel capacity or the leakage rate, which is basically which is basically a measure of how much information or data is leaked or transferred per unit time, right? So like how much private data or let's say the how many bits of the cryptographic keys they are transferred from the sender to the receiver in per unit time. So more number of bits you can, if you an attack or a channel which can transfer more number of bits is better from the attacker's perspective as compared to a channel which has lower transfer rate or lower channel capacity. Okay, so let me cover the introduction part and at least the section one, and then I will take your questions. Okay. So now the question is that uh, what makes an attack a strong or an impactful attack? And similarly, when we say attack, like those attacks which basically rely on side channel or the covert channels. So if you have let's say 10 different attacks, how you will figure out which one of them is most impactful or strongest one. Similarly, uh, in terms of defense mechanism, what makes a defense mechanism more impactful as compared to the other as compared to others? So a strong attack is one which makes no or reasonable assumptions about the capability of attacker, right? So, for example, one assumption can be like the attacker and the victim processes both are co-located, both are running on the same machine. But let's say as compared to that, if you have another attack which assumes that attacker and the victim both are not located on the same machine, so that attack is stronger than the first one, right? Because it doesn't need the co-location. As I said, an attack which achieves the higher information leak rate is more impactful, or it is the stronger one, because then uh, uh, if you can leak the more information, uh, it's mean that you can leak more private data of the victim, right? Lower the rate, higher it will take time to do the leak, right? So because for any attack to be meaningful, you require a minimum amount of leak data is needed, right? So now let's say like if the minimum amount of leak data is, let's say I'm just making up a number, like let's say 1 MB, right? But let's say the attack one, it transfers the minimum amount of leak data is 1 MB. Let's say attack one transfers it in uh, 5 seconds, and attack two transfers it in uh, 20 seconds. Definitely, your attack one is then more stronger as compared to attack two, right? So because lower the rate, higher it will take time to do the leak, which basically mean that attack needs more time to succeed. And if that an attack time needs more time to succeed, it's mean that more time is available to the defense mechanism to detect that whether there is an ongoing attack or not. And if it detects, then maybe it can trigger some how to say uh, recovery mechanism or some defense mechanism. Similarly, a strong or impactful defense is one which will protect which protects your process or your software without lowering the performance of the hardware platform. Okay, so in this survey or in this paper, we are basically talking about it covers only the software attack on hardware. What does it mean? It means that, for example, attacker process learns some information about a victim process, right? So, mean our attacker is also a software process. Our victim is also a software process or a process. Process is in context of systems or computing systems. Process is definitely a software or a code. So this survey doesn't cover hardware attacks, which require physical proximity to victim. For example, power analysis side channels or electromagnetic side channels. Like for example, in power analysis side channels, in one of the paper which we'll cover, it briefly talks about power analysis side channels. So what you can do is like you can do the power profiling, power consumption profiling of a processor by putting some instruments or by putting some tools near to your processor or you're near to the computer, and based on the process profiling you can extract some information. Okay, now let me check if there are any questions. Okay, why does defense against side channel attack cause performance degradation? Okay, Salib is asking this question. Anyone who want to answer this question? Why does defense against side channel attacks cause performance degradation? You can unmute yourself and you can answer, or if you want, you can reply in text. Up
Uh,
to you.
I, I would say primarily because the information leaks happen when like operations are performed on the CPU, so you have to kind of circumvent those and use something else, which just takes more time. It's not straightforward.
Yeah, that's like the basic. That's correct. The basic idea is like if like let's say you don't have defense mechanism and the attacker can exploit the microarchitecture's architectural state. Now what you will do is that you will first try to know that what microarchitecture state is exploited by the attacker, right? And once you know the reason, you will take some countermeasures, right? To so that you can how to say not make that source of exploitation available to the attacker anymore, right? So when you take those countermeasures, it definitely means that you are spending more time. You are doing some extra operations which incur extra latency, and as a result, you will see that there is performance degradation, right? So this is like basic idea, but when you go into more detail, this basic idea, this basic reason that why defense mechanism result in performance degradation, it is valid, or it is applicable to the details of each defense mechanism. We will see later on when we talk about specific details. Okay, can only a program running on the same core get the leak information in a covert channel, or can it be done from out of the same core? Uh, it depends on attacks. So some attacks they assume that the attacker and the victim they are running on the same physical core. So they are like uh, uh, if they are running on the same physical core, and from our previous lecture slides, you know that in one physical core you have two logical cores, right? So if they are running on the same physical core, they are sharing some resources, like for example L1 cache, right? So some attacks they assume that the victim and the process they are running on the same physical core, and then there are some other attacks which relax this restriction, and they assume that attacker and victim are running on the same processor but in different cores. Remember, in each processor, in one processor you can have multiple cores, right? So again, it depends upon the attack, right? So definitely an attack which assumes that the attacker and the victim are running on the same core is more restrictive, or is a weaker attack as compared to the one which assumes that the attacker and victim can run on different cores or even on different machines altogether connected by network. Is it possible to detect if an attacker program is using a covert or secret channel to uh, gather information? Uh, uh, e- I would say yes, because what you can do is like if let's say there is a process which is whose behavior is deviating from the normal or the expected behavior. Like for example, let's say if there is a process which is repeatedly flushing, I think I have explained in previous lecture slides what is flushing the cache line, right? So let's say if there is a process which is repeatedly flushing a cache line or a set of cache lines, right? So this is not a normal behavior, right? So it is a deviation from the normal behavior. So you can then use this observation to make an inference that uh, highly likely this process is like building a covert channel or side channel and trying to send the information. But again, it depends upon how you define normal behavior and how you define the deviation from the normal behavior. But the basic principle is like you can use this approach to detect if there is a covert channel or if there is a side channel. But again, this is a difficult process because for that you need to know the details of how the architectural components work and how architectural components work and how you define the normal behavior. Okay, now let's go to the next slide. So in the previous slide, we have basically talked about what is a communication channel, what is a covert channel, what is a side channel, and also what is how we which type of attack we consider is more impactful as compared to the than what makes a defense mechanism more impactful, right? So now we are going to talk about the classification of the side and the covert channels. So there are basically three types of side and covert channels: timing based, access based, and trace based. So timing based, they rely on timing difference of various separation to leak information. For example, one process, let's say an attacker process, it intentionally performs less or more memory accesses to affect timing of memory accesses by another process which is also running on the same machine. Like let's say you have now, I don't want to draw it, but just visualize that you have a processor in which you have four different cores, right? And each core has two logical cores. So in total, you have eight logical cores, which mean that eight different processes or eight different threads can run at the same time, right? Now, if thread zero, it intentionally issues a large number of memory writes to certain address, and if it does so and then it finds that it is facing the contention, it means some other processes also trying to access the same address, right? So it can it can get some information about behavior of other threads or processes running on the same machine. Access based access based channels. So these channels, they access certain resources, and these accesses perturb the timing of another process operation. Example, so suppose that the uh, an attacker process or a thread, it accesses or probes the cache locations, which is a shared resource, and measures the timing of its access, like hit or miss, right? So, what does it mean? Like, remember from our previous lectures how cache set are indexed. Set are indexed based on untranslated bits from the virtual address, right? So, do you want me to try? So if you remember, how is virtual address divided? So if page size is 4 kilobyte, then 12 bits are used as page offset, right? Page offset. And this is then, so if this is virtual address, so what you will do is that first, uh, like the virtual address is this whole thing, okay? Not only in this arrow. So first you will do the translation. You will look into the page table based on the address, right? And then this will give you physical address, or it will give you frame number, right? Which you will then combine with the offset. And then this will give you the full physical address, like let's say 52-bit physical address, right? Now, when you access the caches, like for example, L1 cache is accessed based on virtual address, not on physical address, right? So the sets in the L1 cache, they are indexed based on the virtual address. Which bits? These untranslated bits, these bits are used. How these bits are used? You divide them into two. Like for example, if you have 64 sets, so 6 bits are used for set index. If you remember from previous lecture, 6 bits are used as a byte index, right? So here you have, like, let's say multiple sets. Actually, this arrow should be pointing here, like, because you select a row or set based on the 6 bits. Now, let's say you have virtual address X, and you have, which is coming from, let's say, process X, and a virtual address coming from process Y, right? So if these two bits are same, the value of these 6 bits are same in the virtual address X and virtual address Y, it's mean they both of them will be indexing into the same set, right? So if they are indexing into the same set, it's mean that uh, you can now you are going to the same set. So it's mean that now in the same set you have in one set you have multiple ways, right? Now, in which way it is occupied, it will depend upon which way is empty or which is least recently used. Let's say both of them end up using this particular way, right? So it's mean they create the contention. So if they create, if there is a contention between process X and process Y, right? So now let's say process X is an attacker, right? So what it can do is, like, let's say it says, okay, I am first going to put my data A here, right? And then I will wait, or let's say it voluntarily releases, it goes to sleep voluntarily. So it goes to sleep, so which mean that it is not running anymore. And then it comes back and it tries to access the same data. So it issues the same address X, right? So if it issues the same address X and it finds that its data is still there, A, it's mean that no one else is accessing the same address, same cache line, right? But if so, which means hit, right? But if there was a miss when it sleeps, when it comes back from the sleep, and it is like running again, and after that, if it accesses this data and finds that there is it issues the same address and finds that there is no data in the cache line and there is a miss, it's mean that some other process has overwritten its data in that cache line. So what information it can get? Oh, so if it was a hit, uh, the data will be rapidly given back to the core. But if there was a miss, the data need to be first brought from the memory and then placed in the cache, and then it will be provided to the core. So based on the timing, it can find out whether it was hit or miss, right? So if it is a hit, which means that if it takes less time to read the data, it will say, okay, now I get the information that this cache line is not overwritten by another process. But if there is a miss, which means if there is a higher time to a higher latency to get the data, so it's mean there is a miss, which means has someone else is also accessing the same cache line. Okay, so this is like pure based access based covert channel or side channels. And trace based is one where a based channel is one which relies on mirroring the program execution. For example, you gather the power consumption trace of the trace after running when you run your program or when you run a victim program, and then you have some kind of setup which measures that power consumption. So this trace-based kind of side and covert channels, they are not covered in the paper. So that's why in this figure, they are just excluding that kind of attack because they require the physical proximity of the attacker or physical access of the attacker to some physical devices or physical tools which actually enable the attacker to launch the attack. But other than that, you can divide the timing based and access based attacks, timing based and access based channels. Using them, you can launch two types of attacks: external timing attack and internal timing attack. So external timing attack is one where the attacker measures the timing of victim's operation, right? Just like I showed you in the previous on the OneNote example, that attacker can no, sorry, that was the case of the internal timing attack, because there the attacker was measuring the timing of its own operation. So it was trying to access its data A. So if it is a hit and like the data is readily available, it's mean there is a hit. No one has ever written that cache line. If there was longer time or longer latency was incurred to access the data, it's mean there was a miss and someone else is also using the same cache line, right? External timing attack is one where attacker measures the timing of the victim's operation, not the timing of its own operation. Any questions? No? What shared resource is often used in access-based side channel attacks? So one example is, for example, L1 cache. It can be a TLB, it can be a predictor. So any resource which is shared among multiple logical cores or physical cores. So for example, L1 is shared among multiple logical cores, right? But L2 is shared among multiple physical cores. Similarly, TLB or branch predictor. Okay. Any other questions before I go next to the next slide? Okay. So why are caches frequently targeted in access-based attacks? Uh, Okay, so caches are frequently targeted. Not only caches, you can actually the security attacks are hardware based or covert based or side based side channel based attack. They can target any shared any resource which is shared among multiple processes. For example, even execution units, or for example, branch predictors, or TLBs, are caches. Now I don't know now. I am not clear whether the number of times or number of distinct attacks which exploits the shared caches is higher than the number of distinct attacks which, for example, exploit TLBs. I'm not sure on that, but uh, logically, I can think that maybe that is the reason. That can be the case because the caches, they are like for example L1, L2, they have more information available in the sense because they have like for example if in L1 you have 64 sets, then it's mean you can store a relatively much larger amount of data or information in L1 as compared to, for example, let's say you have branch predictors, and remember branch predictors, they are shared at the granularity of addresses, right? So the amount of information which is shared among uh, multiple processes through caches is larger as compared to in case of other units, like for example execution units. Which type of a covert channel would be hardest to detect and why? Uh, no, I am not sure on that. I don't have an answer to that, and I don't want to give you any misguiding information at this point. I will check this and come back to you. Okay, so now uh, this slide basically it covers the background, because on top of this background or on this on top of this section they are building the section 3 in the paper, which talks about different characteristics of the architecture which result in information sharing or which result in side channels or cover channels, right? Now, I think that you should appreciate, or maybe you should be able to see it, that the benefit of reading the first paper in our class, because now you already have an idea, at least some idea of what a pipeline is, what are different stages in a pipeline, what is the logical core and what is the physical core, right? So the logical core is, so here they have a typical two-thread simultaneous multi-threading processor, which mean that you have two copies of fetch stage, two copies of instruction stage, but execute stage is shared, right? And then you have two copies of memory stage and the write back stage, right? And as a benefit of reading the first paper at the start of the course, now you know what is the job of each stage in the pipeline, right? So I don't think that I need to explain the processor pipeline. You guys already, if you let me know if you want me to explain this, how processor pipeline is working. Otherwise, I will simply go to the next point. Since this processor uses two-thread SMT, do both threads share the same caches and execution units? Anyone who want to answer this question? OVL is asking that this processor shown on the slide uses two-thread SMT. So do both threads share the same caches and execution units? Anyone who want to answer? This is your chance to, yeah. Yeah, actually they share the same the core. They share the same caches and execution unit, and this is actually clear from the figure. So here you can see, so that this let me select the pointer. So the execution unit, it is shared between uh, two logical cores. And the other thing is, like, if you look at the L1 cache, so it's same L1 cache, it feeds both uh, stages, both stages, fetch stages of like fetch stages of both logical cores, right? And similarly, the memory stage of both logical cores, it also reads or write data from the same L1 data cache. Okay. Why does SMT make timing and cache attack easier than if each thread ran on fully separate hardware? Anyone who want to answer this one? If you want to answer, you can also unmute yourself. That is faster. Okay, I think I will go ahead and answer this then. So, because when you are sharing, when you are like, okay, because someone already answered it. Because if they, let me check the answer. Because if they share resources, then the malicious program can find info about the other separate hardware, will not share as many. So here is the basic point. If you are sharing the resources between any two persons or any two entities, it's mean you are creating the contention. So if you are creating the contention, let's say there is a single book and two students want to read it, right? So only one student can read the book at a given time, right? So if student A is reading the book, but student B is waiting, so at least the student A can get this information that, oh, student B is also interested in the same book, right? So this is some information you can get from the contention, right? So similarly, if you have this, if the execution unit is shared among two logical cores, and let's say both logical cores are executing two separate instruction streams, but the instructions on those stream at a given time, let's say they want to do the same thing. Let's say the instructions both the stream at a given time are add. So it's mean that both of the logical core want to execute their add instruction, but there is only one, let's say, adder, and let's say it is not pipelined. So if the adder is not pipelined and there is only one adder, then only one of those two instructions can go ahead. The other one will be blocked until the first one is completed. So it will now give the information to the other logical core that my competitor is also basically want to do the same, want to execute the same instruction. Okay, so yeah. Okay, now let me go ahead. So first thing about this slide is that we just wanted to cover or explain that how processor pipeline works, which I guess you guys already know. I'm skipping it. If you don't know, let me know, right? So I will explain it. And the other thing is that the functional units, they are stateful functional units. What is meant by the stateful functional unit? It's mean that they retain history, and their future outcome or their next outcome of a functional unit is dependent or is influenced in some way by their uh, inputs, right? So, for example, predictors, reservation stations, and reorder buffer, all of them are stateful functional units. Are one very easy example or very common example is the register file, right? Like let's say the content of the register file at time t0, it influences the content of the same register file in a future time t1, right? So the future output at time t1 or future content of the register file at time t1 will be influenced by the content of the same register file at some time in past, let's say t0 or something in the past. Right? Because inputs are read from the register file and then you perform some operation on that, and then the result of those operation is then written back into the register file. Uh, the other thing which we wanted to talk about in this slide is out of order execution. So out of order execution, why we wanted to talk about it? So because out of order execution is a performance optimization, it allows you to execute the younger instructions before the younger independent instructions before the older instruction, like before they are completed, younger instructions are allowed to go ahead, right? But what is the problem? So that is the performance optimization. But what is the problem? Like it can potentially increase the contention among instructions. Like let's say you have three younger instructions, and two of them are add, and one is, let's say, and, right? So if both of them, if you allow them to go ahead and execute, so it can create contention between the add instructions. Now, the thing here is that in your pipeline, there can be different execution paths. When we say different execution paths, it's mean what path is taken by an instruction when it moves through the stages of the pipeline. Again, it depends upon the type of the instruction. So, for example, if you have an add instruction, definitely it will be first fetched, then it will be decoded, then it will be executed, then it will go through the memory stage, and then the write back stage, right? So now when it is executed and it is an add instruction, so doing add, it takes much less time as compared to doing the multiplication operation, right? So there are like so add instruction will go through the adder through the adder unit, while the multiplication instruction will go through the multiplier unit, right? So they will take two different paths. Now, if I know, let's say I'm just making a very simple case. Let's say if I have uh, two programs and I'm sure that and I know that all the instructions in these two programs are only uh, add and multiplication, nothing else. Either you can have add or a multiplier, and no other instruction other than addition and multiplication, right? Now let's say if I give you an example, let me go back to OneNote. So let's say you have two programs, program A, program B, and both consist of a mix of addition and addition and multiplication. Now let's say in first you have add, 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 multiply, add, add, right? And in the second you have add, multiply, multiply, add, multiply, multiply, right? So now let's say you are just an observer and you are looking at uh, like the execution time of the instruction. You don't know what type of instructions are contained in the program, or what type of instructions constitute your program, right? But you can only observe the timing of like how long it takes for an instruction to complete, right? So let's say add takes, I'm just making it simple. Let's say add takes one and multiplication takes, I'm just making it an extreme case. Multiplication take 10, right? So when the program A is running, you observe that first instruction is completed in one cycle, the next is completed in one, the next is completed in one, next is completed in 10, 1, 1. You can get, and then when you look at the uh, instruction timing of the second program, you found that first instruction completes in one, then in 10 units, 10 cycles, one cycle, 10 cycle, 10 cycle. Just by looking at the timing, you can construct the program. Again, this is a toy example where we are like making several assumptions that our program is consisted of only two type of instructions, add and multiply, and also like there is a significant difference between the time needed to perform the, sorry guys, sorry guys, just let me give a 1 minute. Sorry, I got a cramp in my leg. Sorry for that. Okay. So here we are making the assumption that both of the programs, they are consisted of like only add and multiply, and there is a significant difference between the timing of the two instructions. But this toy example is sufficient to convey the idea that by just by looking at the timing or difference, like fast path and slow path, you can get or extract some information about the program which is running on the machine. Okay. The other thing is that, as I said, like if you have the function, if you have sharing of functional units, then it's mean that there will be contention between the sharers. So if there is contention between the sharers, so one participant can get information, some information about the other participant in the competition, right? Or in the contention. Okay. So any questions before I go to the next slide? No? Okay. Now, what are the characteristics of processes which lead to the microarchitectural based side channel, the side channels or construction of microarchitecture based side channels? So one of that is the instruction execution timing, which we basically have talked about already, right? In context of our example of like two programs consisting of add and multiply instructions. So processor hardware, they perform different computations. So some computations are fundamentally simpler than others. For example, in our case, doing add was simpler or faster as compared to multiplication, right? Another example is, for example, logical operation and or NAND. They can be executed in a single cycle. Similarly, arithmetic operations such as addition is also fast as compared to multiplication and other complex operation which require multi-cycle execution. So the fast and slow path, they lead to the information leaks as execution of different instructions take different amount of time. Now, how can we like if I go back to the same example here on OneNote, so we are leaking the information because of this fast and slow path the execution path taken by the instructions, right? Now how can we get rid of that, or basically how can we avoid the information leakage due to this instruction difference in the instruction execution time? So one way is like which is like definitely a very naive way and very how to say performance costly way, that what you can do is that you can make or you can require all instructions to complete in the same amount of time. So basically which mean that you complete add instruction also in 10 cycles. Actually, you will, for example, you complete it in one cycle and then you keep waiting for next 9 cycles, so that there is an illusion that the add is completed in 10 cycles. So if now all the instructions are completed in 10 cycles, there is no randomness. So if there is no randomness, there is no information. So if there is no information, so nothing is leaked. So because now when I will look at the instruction completion time of each instruction, so I will see 10, 10, 10, 10, 10, 10. So it will give me no information whether the instruction which is executed is add or multiply. Okay, where is the slide? Yeah, here. So how can we eliminate this fast and slow path? Maybe by equalizing the timing, but then it will cause major performance loss. Why it will cause major performance loss? Because earlier you were taking only one cycle to complete that. Now if you are saying that you are equalizing timing of all instructions, and let's say you are saying all instructions take 10 cycles. So if earlier you were completing, let's say 4 adds in 4 cycles, now you will be completing those 4 adds in 40 cycles. Okay. Now, so one characteristic is that there is existence of fast and slow execution path in your microprocessor. The other thing is, the other problem is their contention of between the functional units, right? So the issue is that your processors, they are constrained by area and power budgets. So you cannot have like a chip with infinite number of transistors or with infinite power budget, right? So that's why what designers do is that they reuse or share the functional units instead of duplicating them, right? So if there are functional units which you think that they are not used all the time by a thread or by a process, so what you can do is that you can share them among multiple logical cores. Remember, each thread runs on one thread run on on one logical core, right? So when I say that you can share the functional unit among threads, it's mean that you can share the functional units among logical cores, right? So here is an example. So in case of like simultaneous multi-threading, so multiple pipelines, there are multiple pipelines per core, but they share execution units, just like we have seen in the previous slide that execution units are shared among the logical cores. So why we do so? Because the workloads are the programs which are running, they are usually mix of instructions. So for example, maybe program A does addition, program B does memory access, right? So when if you are sharing the execution unit, or you are sharing the uh, uh, let's say the execution stage of the pipeline in which you basically have those execution units. So then if program A is let's say doing addition, and program B wants to do the memory access, or let's say program B wants to do the multiplication, so both of them can enter the execution stage at the same time, as long as they are using different functional units. So this reduces the contention, but this reduces the contention when the two workloads or two threads, they are asking for different functional units or execution unit in the in the execution stage. However, the problem is when both pipelines are both threads. We say pipeline, it's been logical cores. If the both logical cores, they need the same unit. For example, let's say adder, both of them want to perform addition or multiplication or some floating point operation. So what happens that one of them will be asked to stall. So if one of them will ask to stall, it's mean that there will be timing difference. So timing difference will occur. So other like uh, so if it is asked to stall, it means that it gets the information that the other logical core is also asking or demanding the same unit. So it gets some information about the other logical core or the other thread running on the logical core. So this timing condition leaks information about what the other programs are executing. So now uh, how can we avoid, or how we can mitigate this information leak? Definitely by removing the source of the information leak. What is the source of the information leak? It is sharing of the resources, right? So if we avoid the sharing and we duplicate the resources, or we duplicate the hardware components, right? So we can then we can avoid the contention. So if we avoid the contention, we can avoid the information leak, right? Uh, I think one of them asks you the question like why it is expensive to uh, defend against uh, side channels or covert side channels, covert channel or side channels, right? So because and I gave you a principled answer, but here you can understand it in more depth. Like if you try to address the source of that uh, channel, which is in this case is the shared unit, then you need to remove the reason or the source of that channel, which is by to duplicate the hardware. Now, if you will duplicate, it will become more expensive. Okay. So if you now duplicate the hardware, so yes, you can do that, but not only it will be expensive in terms of like it will take more space, but it will also consume more power. So for example, simultaneous multi-threading, it provides larger performance gain with small area overhead, right? So which mean like if you are sharing, for example, the execution unit, the area overhead is only like 6% larger than the single thread core, like where you have only single thread. But if you have two logical cores with their execution shared, you incur only 66% larger overhead than a single core, a single pipeline, right? Single logical core, but you have significant performance gain. Now you cannot how to say sacrifice that performance gain by saying that okay, I will not share any resources. I will duplicate the whole pipeline where even the execution units are not shared. Now what will happen that your area overhead will be much larger than 6. It will be actually become double, right? At least in the context of the pipeline, because you are duplicating everything, right? So maybe you will get the since you still you will get the performance gain because you have two independent pipelines running at the same time, but your area overhead will be significant. So that's why your sharing of the resources, if SMT is an example of that, is likely to remain common in your all the processes, and you are not going to like get rid of it. So this is another example of uh, like we yes we want to develop the mitigation against side channels or covered channels, but without sacrificing the performance, right? So this is the summary of the slide, that you have functional unit sharing, and as a result of this, there is contention among threads or logical cores, and this contention leads to the information leakage. Okay, we still have like 15 minutes. Uh, Another characteristic of processors is that lead to microarchitectural based side channel is the state dependent output of functional unit, right? Let me explain it through an example or simulation, and if we have time, then I can come back to this slide. Otherwise, after that simulation, you can read this slide on your own and you will understand what I mean here, right? So we will try to understand it through an example of a branch predictor, right? So uh, this is not the branch predictor we are going to talk about. This is the building block of the branch predictor we are going to talk about. Actually, it is also a branch predictor, but we are going to talk the YePAP predictor, which builds or which uses this 2-bit predictor. So let's first talk about this 2-bit predictor. So remember why we need prediction. So if you have a branch instruction, for example, if else statement, so where you test a condition. So if the condition is true, let's say if condition is true, you execute, you start fetching the one set of instructions from the, let's say, if block. If condition is false, you need to fetch the instructions from the else block of the code, right? Now, if you remember from previous lectures, we cannot wait for the branch instruction to be executed actually, and to find out whether the instruction is whether the condition is true or false, because it means what? Remember, when an instruction is executed, it first enters in fetch stage, then it goes to decode stage, then it enters execute stage, then it goes to reorder stage, R stage, right? And then it goes to the commit stage, right? So when if when the let me go back. Do you want me to explain this, or you have that knowledge already in your mind, and I can simply go ahead and start explaining how this branch predictor, how this 2-bit predictor works? Please skip. Okay, good. O- Okay, okay. Okay. So this branch 2-bit branch predictor tells us that what prediction we are going to do. So whenever you see a branch prediction, a branch instruction is fetched, you perform the prediction, right? And how you perform the prediction? By storing a counter, by having a counter which has only 2 bits, right? So it is a 2-bit counter. So if it is a 2-bit counter, it can have only four possible values: 00, 01, 10, and 211, which is in decimal form is 0, 1, 2, and 3, right? So you initialize that counter with value of 1, right? So here you have this boundary line shown in the dotted form, right? So if the value of your counter is less than this boundary, you will predict that branch will be not taken. If the value of the counter is above this boundary, then you will predict that the branch will be taken, as shown here. Prediction taken, prediction not taken. Right? Now let's say that you have the branch instruction and you look at the counter, and the initial value of the counter is 1, and it is saying that uh, uh, here I'm just lighting P is for prediction and A is for the actual value, right? And let's say the prediction is that not taken, right? And when actually the branch is resolved, it turns out that the branch was taken, right? So if it is taken, so what we do is that when the branch is resolved at that time, so if the actual value is taken, we increment the value of the counter. So it goes from 1 to 2, right? Now, next time, let's say you again do the same branch, like you same branch instruction is again fetched, right? Maybe you are executing in the a loop, and in that loop you are executing that branch instruction again and again, right? So that branch instruction is again fetched. So you look again at its counter. the value of the counter is 2, and it means what? The branch will be, so here prediction is taken. So we are making the prediction that the branch is taken. And let's say that the actual value is also taken. So actually the branch is also taken. So if the branch is also taken, so actual is taken, we increment the branch, the value of the counter again. So it becomes 3, right? Next time, let's say in the next iteration, you again look at the counter, the value is 3, and you are doing the prediction taken because it is above this boundary line, right? And let's say that actually the branch was not taken. So if the branch was not taken, actually, so then you decrement the counter as shown here. So it reduce it to, so every time when branch is taken, you increment the counter, and every time when the branch is not taken, you decrement the counter. And the since 2-bit value can have the minimum value of 0, 2-bit counter can have minimum value of 0 and maximum value of 3. So when you reach at 3 and again the branch is taken, your value saturates. And if you are at 0 and your branch is not taken, so your value again saturates at minimum 0. Okay. Any question regarding this 2-bit counter, 2-bit predictor before I go to the next slide? Because branch prediction keeps state over time, could an attacker potentially influence or probe these states to create a side channel or help with some other attack? Yes. Actually, in the next simulation, I'm going to explain that. Exactly, I'm trying to answer this question. Any other question other than this one? Okay. Everyone is clear on how this 2-bit predictor works? Silence mean everyone is clear, right? Then I'm moving to the next slide. Okay. So this YePAP predictor, this actually works. It has like two different tables. One is called history table. The other is called pattern table, right? So in history table, you have multiple entries, and each entry is a shift register. You know what is a shift register? Anyone who doesn't know what is a shift register and how it works? Silence. For silence, I'm assuming that everyone knows what is a shift register, and I'm moving forward. Okay. So each entry in the history table is a shift register. It can be of like any size, but for our example, in the upcoming slide, we will assume that it is a simply 2-bit shift register, right? And how this history table is indexed, like how you access an entry based on the address of the branch instruction, right? And then, so using the address of the branch instruction, you go to one entry of you go to an entry of the table. That entry of the table will give you some value, right? And using that value, you index into a second table, which is called pattern table, right? So this each entry in this pattern table is actually a 2-bit predictor, right? Which I just explained earlier, a 2-bit counter, which I just explained in the previous slide, right? Now, okay. Uh, Now let's have this example now here. So suppose that you have two branch instructions, A and B, right? And let's say they belong to the same, these are two branch instructions in the same program, right? So address of A is the address of the first branch instruction, B is the address of the second branch instruction. And what is this sequence of T and T and T and T T T? So this is like actual pattern, like actually whether this branch is taken or not. So for the branch which is at address A, the branch instruction which is at address A, it is first time taken in like when it is resolved, it turns out that the branch is taken. And in the second iteration, it turns out it is not taken, again taken, not taken, taken, not taken, and so on. So alternative taken, not taken. Branch, which is at address B, it is always taken. So here we are assuming a program which is executing in a loop. And in the body of the loop, you have two branches, one at address A, the other at address B. And these are the patterns, actual patterns for these branches. Like A is alternatively taken, not taken, taken, not taken, and B is always taken. Okay. Now, how this YePAP predictor is used? Remember, we have two tables, history table and pattern table, right? Yeah. I am going to explain this. How can attacker mistrain the branch predictor? I am actually trying to explain that. Okay. This slide and the next slide will explain it. So first, let's see the training. How these branches, how the YePAP predictor is trained, right? And then we will see how can do the how an attacker can do the mistraining, right? So so first for A, you use the address of A to index and find an entry in the history table. Let's say it points to this entry, right? So you get the value of this entry, which is 00. So now you go to the second table, and which entry of the second table? Entry 00, right? And then you get its value. Remember, each entry in the pattern table is a 2-bit predictor, right? So what is the value initially? All the 2-bit counters are initialized to 1. So its initial value is 01, right? So what is the prediction? If you remember from the previous slide, any value like lower than the boundary, which was if there is value of 0 or 1, it's mean the prediction is not taken, right? So prediction is not taken, and the actually the branch is taken, which you can see from here, right? So there is mismatch between actual value and the prediction, right? That's why I showed it in the red color, right? Now remember that each entry in the history table is a shift register, right? So what happens is that you simply from the right side you feed the value of actual branch resolution. So if it is taken, you feed 1 from the right side. If it is not taken, actually you feed 0 from the right side, right? So it will become 1, 0, 0 will 1 become 0, 1, right? Because it was taken actually. So it means taken is indicated by 1. So you put a 1 from the right side. So the shifter, it is shifted, the value is shifted to left and it becomes 0, 1, right? And again, this was what? This is a 2-bit predictor and the actual value was what? Taken. If you remember, we said in 2-bit counter that whenever the actual branch resolution is taken, we increment the value of the counter. So it was from 1, it becomes 2, right? Okay. Now, let's say that after A, oh yeah, thank you for reminding. Yeah, there is a class participation form. Okay, let me stop here and I can start from the same point in the next class. Uh, and I will actually encourage you to at least go through these two slides on your own. I will go over them in the next lecture, but still I want you to go through them on your own so that you at least get some idea and it will be relatively faster for me. Okay, so let me stop here and uh, share with you the code for the access code for the class participation form.